Hi everyone. So please welcome Jithu for our 14th Indus meeting. Jithu is a PhD student and a Prime Minister Fellow at the Indian Institute of Technology, Indore, and currently working with Professor Bhargav Vaidya. He joined IIT Indore a couple of years back, and he did his masters from CUSAT Kochi, and he was also a CSIR fellow and ranked one in CUSAT in his masters. So his current research interest is application of AI and ML in forecasting the space weather and related topics. And we also had a great time last month when both of us was in ESPM meeting. So saying all this, and also, another important thing is that Jithu is eager to take questions during the talk. So please feel free to interrupt him whenever you have any question. So saying all this, Jithu, the floor is for you. You can start now.
Thank you, Devesh. First of all, I would like to wish everyone happy Diwali. And I would also like to thank Indus for giving me this opportunity to present my work in using artificial intelligence for space weather modeling. Today, I will be presenting our recently published paper, the surface flux transport modeling using physics-informed neural networks. So this was done with collaboration with the people given like Bhargav Vaidya, Sain, Vishal, and Mark. Going straight forward, I would like to motivate everyone on why we need to have the surface flux transport modeling, or basically why do we need to understand the magnetic field of the sun. Okay, so I think my slides are moving. There are many space for the drivers, like let it be solar wind, let it be CMEs or solar flares. Everything is connected to the magnetic field of the sun and how the magnetic field evolves over time. And this magnetic field is directly related to different physical processes that happens on the solar surface. So it is very important to understand the evolution or how the magnetic field on the solar surface evolves, and how it what all physics is in undergoing in that, if we want to fruitfully forecast, or if we want to understand the space weather completely. So with this intention, we wanted to study the solar magnetic field. And why do we need artificial intelligence? The first thing is that in such a system, there are different physical processes that I'll be discussing in a couple of slides ahead. And there is a different scales, like length and time scales inbuilt in all these processes. So it is very hard if you want to do a fruitful complete simulation in incorporating all the length scales and all the time scales. So we wanted to try a artificial intelligence based non-trivial solution, which could kind of bypass this numerical simulation setup, and then we could get results. So to begin with, we wanted to try a artificial intelligence based and numerical, traditionally existing numerical technique, and we wanted to compare them and see how or both of them have their own advantages. So in what all points that they would be better among the two. So that was the thing that we want to check first of all. Going further, what is surface flux transport modeling? As you all know, the magnetic field on the solar surface is like affected by different physics. And what surface flux transport modeling does is it tries to mimic the evolution of the radiant magnetic field on the solar surface using different processes. Now, the different process comes from the induction equation. On the right side, you can see the induction equation that has been cut short into different processes. It takes care of the advection, diffusion, decay, and the source terms. We can see what each terms kind of mark through. In the advection term kind of realizes the differential rotation and the meridional flow that we see. The differential rotation, as you all know, the different layers of, like if you see on latitude, different layers, the sun rotates with different angular velocity. So that's what's differential rotation. And meridional flow is the poleward flow because of different convection zones. So because of that, there is a poleward push of the magnetic field and plasma from the equator, and which is termed as meridional flow. It has been very well studied. We have the profiles that comes from different methods, mainly from observations and helioseismology, on how these things are different. And we have an understanding, and we have different functional forms for all these things. Going further, you have diffusion. Diffusion mainly takes care of the random motion of the supergranules. As you all know, solar surface has many supergranules of different megameter size, and they kind of moves, and it kind of collapses, and you can see the different polarities getting diffused and all those things. So this process is being captured by the diffusion term. You have the decay term, which kind of takes care of the radial diffusion, like you have the magnetic field moving towards the upper atmosphere from the solar surface. So that is taken care by the decay term. And the last, the source term, takes care of new active regions and new magnetic flux coming from way down the earth, way down the sun. So these are the four different physical processes that typically a SFT model kind of mimics, and you kind of interplay all these different physical processes, and we try to understand how the magnetic field is going to be evolving. Here you can see the actual SFT equation. I have shown the induction equation here and different terms. Now, if we do this del dot and all, we will get the specific form of SFT equation. The first one is the 2D SFT equation, where lambda is the latitudes and phi is the longitudes. So we kind of simulate on the theta phi plane, the lambda phi plane on the solar surface at a constant r, that is at the photosphere or the solar surface. If you kind of average this 2D SFT equation along the longitude, you will get the 1D SFT equation. There are no phi's in the 1D equation. This 1D equation is mainly studied to kind of understand the polar magnetic flux values, and also to study the how strong will be the next polar cycles. And all, there have been many studies related to how the polar magnetic flux of a cycle of a solar cycle is related to the upcoming cycles. So for such studies, people have used the 1D SFT equation very prominently, and the 2D SFT equation can be used to actually evolve a specific active regions on the solar surface itself. So what we kind of try to do is we do try to solve both these equations in different ways. One is a standard numerical way, where we have used different solvers that will be showing next, and in the other way you have an ML technique that I will be explaining further. So the aim of this project was to solve these two equations at different with different boundary conditions and different initial conditions, and using different methods, and to compare how these methods work with each other. Now, why do we need this? We can kind of use this SFT equation to produce the magnetograms of further in time, which then can be used to predict the particle properties at L1 point. As you all know, there is already an existing Swasti framework, which kind of takes the input magnetogram at the solar surface, and it can be used to find the particle properties at L1 point. Now, using the SFT, we can try to evolve the current magnetic field to find a future magnetic field, future magnetogram, which can be used on the same Swati framework for forecasting and finding the L1 properties at a later time. So this is the aim. It's the aim of the project is to forecast the input of the Swasti framework. Now, I have told that we have used two methods. The first method is the numerical scheme, in which we have separately incorporated two different sub schemes. The first scheme is a normal explicit scheme. It's a textbook kind of scheme, where you have a RK2 time solver. It's second order in time. You have Van Leer scheme for advection and tridiagonal solver for diffusion. I'm not going into details of what these schemes do. I would like to say these schemes are very stable with shocks, as well as these schemes are second order in space. So totally the scheme is second order in space and time. In the second method, in the second sub-scheme, we have used the RK-IMEX scheme, which is Runge-Kutta Implicit-Explicit scheme, where you have both the implicit and explicit solvers for making the solutions better, better incorporating the flux values and better incorporating the shock values, if any. And it also gives a second order in space and time approach. So these two methods are just two different numerical methods. One is a textbook method, and one RK-IMEX is like not very old method. So it's a better way of solving the solution. This is the numerical scheme that we have followed. The artificial intelligence method that we have used is physics-informed neural networks. I would like to spend a bit of time here explaining what it does. You know that if you can see my pointer, yeah, I think you can see my pointer. So a normal artificial neural network kind of has this much part where you have the input layer, you have hidden layers, you have the output layer, and you have loss function. In the loss function, the data will be fed, and the data kind of treats, helps to explain how the network should be working. The aim of the network is to reduce the loss function. The loss function, how it's calculated, I'll be showing next. What in physics informed neural network, what it does is, if you have anything other than data in a normal neural network, you have only the data to work with. So the idea is to fit the data however possible. So in physics informed neural network, what they have done is that if you know something more about the system, like if you know anything more, like if you know the differential equation that's following, if you know the physics that is being incorporated in this specific system, or if you know the initial or the boundary conditions of the system, then you can include these things also into the loss function. Including these things more into the loss function will kind of reduce the parameter space already available for the neural networks, making it easier for the neural network to learn what is actually the solution. So instead of just trying to fit the data, it will kind of try to fit the data along with following some equations that we know. So this kind of helps us to put all the information that we have into the specific neural network training system. In this specific case, I would say the differential equation, we all know that the specific differential equation that we solve is the SFT equation, 1D or 2D specifically, whatever is the that current aim. The boundary condition we know, let's say if you are moving towards the poles, you have an outflow kind of boundary condition. And if you are going through the longitude in 2D runs, you know that it should be a periodic boundary condition because the sun is like completing the circle. So once we know the boundary condition, we can tell the neural network that, okay, whatever B values that you give, it should follow these boundary conditions. And that's what we need. Since we know the differential equation, we can tell the neural network, it's kind of telling the neural network that, okay, this is the differential equation. We know how the magnetic field should be changing with time, what should be the temporal elevation of time. We know dou B by dou T. So the solution should follow this condition also, rather than giving any fit value for the magnetic field. So it's like reducing the available parameter space, making it the solution better and better. And if you know the initial condition, we can input that also, telling the network that, okay, this is the initial condition. You should work with this initial condition and it should be evolved further. So it's like constraining the network on how much or how much the values could deviate from each other. That we are giving a constraint to the solution magnetic field B here in this specific case. And that's how this specific network works. Now, how the loss function is calculated. This is how the loss function is calculated. You have a loss term here. This is the loss function. The capital theta corresponds to a specific hyperparameter set. So for a given architecture of the neural network, what we call the hyperparameter is like what should be the length of the hidden layers, what should be the size of the hidden layers, and these things are called hyperparameters. So once we set the hyperparameters, we calculate the loss function as how much the initial values are different, that comes in this error, how much the boundary conditions are different, that comes in this error, and how much the equation is followed itself, that comes here. This F is actually the SFT equation itself equated to 0, that all the terms has been taken to one side and the final result should be equal to 0. That's why anything that's left in the equation will be treated as an error value. So the total loss function is calculated by superimposing all these three parameters with each other. Now you can see different weights here. These weights kind of says how important each parameter is to specifically solving this equation. So we have actually set up a optimizing scheme to find out what should be the optimum values for all the weights, and that's how we kind of fix the weights. And once the weights are fixed, you know how to calculate the loss function. And once you have the loss function, we can kind of uh, train this network to kind of learn from the input and then find the output value. So this is the overall structure, how this works. Okay. Going forward, once we had this system, we had to validate the codes. For that, what we did was we took two different setups. The first validation that we did was to take the BMRs and try what each have tried to put the BMRs at different locations. Sorry, BMR means bipolar magnetic regions. That's how in a SFT code, how we put source terms are. We consider that there are two, a positive cell and a negative cell, which kind of corresponds to the active region, and we kind of optimize the BMR in such a way that the total flux is equal to the original flux of the active region. That's how SFT sources are done. Now, we put these source terms at different locations, and we trying to find how these magnetic field, the BMRs evolve with time. And we did a comparison with what each did. I think you can see my cursor. So this is the result from each paper, and this is our results. We did a comparative. We did a quantitative comparison itself, and the errors were very less. And we kind of validated the code, how good it, or how like it's working okay. We did this with both numerical as well as the pins method, so that we can make sure that both the methods are working good enough. The second test that we wanted to do was an analytical test. In the analytical test, what we did was we have already a system. DeVore found this in 1984, that if you give a specific velocity profile and a specific, you can have a specific analytical solution. So this kind of gives us a analytical solution where we can compare both the methods one-on-one. Because in normal SFT equations, we don't have an analytical solution, since the inputs are not very like does not follow any functional form very specifically. You can kind of fix functional forms, but it won't be perfectly correct. So this specific analytical solution was found in a very old kind of matching, and we can use the specific analytical solution to compare both the methods one-on-one, by which we will be able to compare what is happening with both the methods. Now, once compared, this is a specific timestamp in your right side. You can see that the errors due to different analytical solution is given in the pink color. Different numerical solutions are given in different colors. These numerical solutions are from different resolutions. You can see the black line which corresponds to the pin solution. So you can see that the pin solution kind of corresponds very good with the analytical solution, and the numerical solution, as we increase the resolution, it comes closer and closer to the analytical solution. This is expected for any numerical method, that if we kind of increase the resolution, then the method has very less numerical diffusion, with which the solution comes closer and closer to the analytical method. In the left side, you can see how the error was changing. You can see the pins error for the with the red line, and the blue line corresponds to the error corresponding to RK-IMEX method. You can see the errors are coming down and down on increasing the resolution. This is what we expect from any numerical scheme. Now, one thing that we were very much interested in is that here we have shown the magnetic field. We wanted to see how the flux will be affected because of the numerical and the pins treatment. Because the very important thing about any classical methods is that there will be numerical diffusion. This numerical diffusion comes because of the gridding, and we have different the differential equation, like the differentiation is done from grid to grid, which kind of makes some loss in the value. It's called numerical diffusion. So numerical diffusion could affect your total flux value, because if your method is more numerically diffusive, then the total flux that you had initially in the system will be lost as you go further and further, not because of any physical process, but because of the scheme itself, if you are having a very diffusive method. So on comparing diffusion and the flux, we found that the flux errors are very less in a pins run. You can see the red line corresponds to the pins value, and here you can see the corresponding error. This is the flux value, and this is the percentage error at different resolutions, and the pins error. You can see pins had almost 1% error only, and as we increase the resolution, we could find better and better resolution runs. gave you better and better flux conservation. Now, what does this mean? It means that if you have some magnetic flux on your system, and if you run a normal numerical setup, which is diffusive, normally people use first order space and time methods, maximum second order. We have used a second order space and time method, which is better. But in that case also, we were able to find that the flux is being lost in the system itself because of numerical methods, not because of any physical process. So there is a flux loss in the system just because of the numerical scheme that you use. And in pins, you can reduce that because pins does not have a mesh dependence. Now I would like to concentrate on this point that pins does not have a mesh dependence. Like in pins method, what you do is you can calculate the derivatives very easily. I would like to go back and show you specifically what happens. In pinch method, you see you can have the output magnetic field here. Now, in the differential equation, you have the differentiation, the gradient of B with respect to lambda, phi, and T. Now, normally in numerical methods, you take grids and you calculate the difference, and that's how you calculate the differentiation. But in this specific case, you see the magnetic field is connected to the inputs by functions. These each arrows corresponds to activation functions. So these are all functions that we know, and we know the derivative of these functions also. So this input is connected to the output as a function. So you can just calculate the derivative just by taking a chain rule function. So it's just a functional value. And since we are using all functions here, there is no loss because it's analytical function. You know the correct derivative. So you know the correct what is the differentiation of B with respect to lambda, or differentiation of B with respect to phi, or differentiation of B with respect to the time. We exactly know the values. So there are actually not at all no numerical diffusions involved in this process. And that's why we are having a very less flux error in this specific case. Now, once we had understood how this pins works, we wanted to try it on normal questions. Like, before that, once we had an numerical setup and a pin setup, after comparing these two, we wanted to try that if we change the parameters of pin, because there are many hyperparameters involved. So what happens if we change the hyperparameters itself? On changing hyperparameters, what we found that our optimized system was working good enough, because whenever you change the hyperparameters from our optimized system, we can see that the errors are increasing, the red line corresponding to the architecture that we are using for the pins run. And these other values, you can see correspondingly what are the small changes that we made to the hyperparameters. We made small tweakings so that we can see how sensitive are each hyperparameters and the solutions. And we found that the best network that we had was the one we are using itself, which we found by optimizing different runs using a process called Gaussian process-based Bayesian regression. And this correspondingly flux errors. Now, going further, we did the same run with a 1D SFT equation. We followed the Petrovay 2019 paper to get, it's a linear run. And like each cycles are corresponding, like it's the same, all cycles will be the same. And what we found was, you can see that there is a change in the polarity reversal time just because that more flux is available in the system. Because more flux is available in the system, because of more flux conservation, the flux is moving towards the poles almost completely, which kind of helps in the delayed polarity reversal. In normal classical runs, what happen in numerical runs, what happens is already in the system as part of the solution, the solver itself, some flux is being lost. So the actual total flux that was input in the system is not moving towards the poles because it's lost in the intervening solver calculations itself. So with pins, we were able to get a better flux conservation. We did the same. If you can see a timestamp, you can see how the solutions change. And also in here also we see the same things. Like if we check with different resolutions, as the resolutions increases, the solutions approaches the pin solution. And also, since there was no analytical solutions available, we did a comparative study with the pins and the numerical solution. And what we found that the numerical solutions are approaching the pin solution, which corresponds to the reducing error on increasing the resolutions. Going further, after doing an analytical run, a 1D run, we wanted to try what happens if we use 2D methods, the 2D SFT equation with pins and numerical scheme. And this corresponds to that. We initiated a normal bipolar magnetic region, two Gaussian one positive and one negative source, and we tried to evolve it for different with both pins and numerical schemes, and we found these two results which are very much comparative. The errors were very less, corresponding to almost 1 to 2%. This corresponds to the highest resolution that we had, which is like almost 2048 was the resolution. So that's very high resolution. With that very high resolution, we were able to get very comparative results. And if you're going for further lesser resolutions, then there is a flux loss, and we were able to see more error. So further, as we tried on 1D and 2D, next we wanted to try with some original active region. So we took the specific active region AR7978. There is a reason why we took this specific active region, because this active region was, it's an old one, 1996, and it was available for multiple CR runs. So it was visible for almost 3 CR runs, 3 plus, you can see very small in the fourth one also. So since this was a very strong active region which sustained for a long time, we will be able to check the flux values, because mostly the other active regions die out very fast. So that's the reason why we studied with this specific active region, but this can be repeated with any other active region. And what we found that we used both the pins method as well as the RK-IMEX method. And with the pins, we were able to reproduce the results with almost 2 to 9% of flux error at different timestamps. So here I would like to conclude what we did, that we kind of used pins method to study the advection diffusion equation, specifically in 1D and 2D setups. We wanted to kind of understand how the pins will be responding to advection diffusion equations, and we found that okay, it works good. The flux conservation is better, and once you have the hyperparameters tuned, you don't want to change, even if you change the polarity of the BMR, or if you change the initial position where the BMRs are inputted. It does not matter, your pin setup is going to work. One limitation, big limitation that we found was that for pins, whenever you change any of the physical parameters, like if you want to run with another, let's say decay constant, or another value of diffusion, or let's say another value of meridional flow, and another functional form of meridional flow, then you will have to tune the pins for, you will have to tune this architecture completely. And also you will have to retrain the pins method, because one pins run is like a one simulation. So if you want to kind of change the simulation parameters, then you will have to run the simulation again. Just like that, pins has to be retrained again whenever you change any of the physical parameters. This is one limitation we found, and we are still working on how we can kind of circumvent this specific issue of retraining it whenever you change any of the physical parameters. But if you take computational time also, even with the retrained value, if the training usually takes around less than an hour for SFT runs of years, which takes almost similar time on a CPU with RK-IMEX methods also. So they like it's almost 20% difference only, like almost 20% time advantage, computational time advantage only with pins. But we expect that if we can kind of find a way to retrain the method for we kind of circumvent the retraining method, then it could become very much computationally better compared to any numerical runs. So that's what we are working in. So these are some of the references that we have used, and thank you. And I'm open for questions.
Yeah, it was a very good talk, Jithu. Yeah, the floor is open for questions. Anyone can raise their hands. Yeah, I guess someone raise. Yeah. Oh no, Pratik is just clapping. Yes, sorry.
Okay. Thanks, Pratik.
Yeah.
Nice talk, Jithu. Yeah, thank you.
Yeah. Shri raised her hand, so yeah, you can go ahead, Shri.
Hi, Jithu. Nice talk.
Hi.
So I just have a very basic questions. If there are these are for by I mean BMRs. So what do you expect if there would be more complexity in the, let's say for quadrupolar? If you are starting with some event like that, or aiming for those kind of events, then what do you expect? What pressures you expect they would be changed?
Okay, if I understand the question correctly, you mean if you are using some other, let's say, a different initial condition, then
Yeah,
how the network will be
yeah,
changing. Yeah, so actually, you don't want to change the architecture of the network. So we have actually tuned the network. We have used a different optimization technique to tune the network for any input condition. So you don't want to change the architecture. It will work good. The only thing that you have to do is retrain the network. So because since you are changing the initial condition, the whole problem has changed now. So you will have to retrain the network again to kind of incorporate the new initial conditions. So since the initial condition is changing, you will have to run the network again. That's all. You will have to train the network again. We have tried with different input conditions and different forms of sources as well as different polarities. And we have tried all these things, and the network works good with all these things.
okay. So, do you expect like there will be some? I mean, have you or are you planning to consider some looking for some differences in any hemisphere changes or something like that? Or
Okay, for
they don't matter, like northern and southern for a long-term
no, no.
studies like that.
Yeah, so we have tried with different like changing the hemispheres also. So the network goes good. There are no issues. So that's one thing. And about long-term studies, yeah, we are planning it and we are currently working on it with one other group on doing a long-term study with the specific network itself.
Yes. Thank you.
Thank you.
Jithu, I have a small question to you.
Yes, there is.
Yes, so you have mentioned that in your, I guess, slide number 15 or so, that like some of the loss in magnetic flux is not because of some physics inside it, but of the like some kind of tools you are using or in
Yes,
your, yeah. So
yes.
would you please explain it a bit?
Yeah, sure. So let's say in a normal numerical scheme, like numerical scheme in the sense, let's say uh, the Runge-Kutta schemes that we use, or normal, let's say, how do we calculate the derivative? I think I will go back somewhere to the equation so it will be easier to understand. Yeah. So you see, when you calculate this derivative, let's say dou B by dou T, so you have BR, which is the radial magnetic field at one time and the other time, and you subtract it and you divide it by delta T. Now, ideally, delta T should tend to 0 if you want to get the correct derivative. That's the idea. Now, you can never get delta T equal to 0 since these are all computation. So you are having specific grids. So because of the gridding, you will always have a specific value of delta T, which is not equal to 0. So this thing is taken care by the resolution, that how small resolution that you can go. The smaller and smaller resolution you go, delta T is going the small nearer and nearer to 0, which gives better value of dou B by dou T. But it's not computationally possible to do like delta T tends to 0 because it will be very expensive. So what people usually do is, like in SFT and all, people take delta T to be 1 day usually. Like usually people run with delta T as 1 day. Now you have a delta T as 1 day, which is not equal to 0. So always there is going to be an error with corresponding to the specific calculation. This is called numerical diffusion. So this specific could affect the total flux values.
Okay. Yeah, so okay, now we understand. So it
Yeah.
will
So
affect, but yeah, so in a sense, since the scale of the like the procedure is smaller in a sense, or sorry,
yeah,
larger
if
in a sense, it will affect the overall flux of the field.
yes, so
It will
yeah,
reduce in a
normally not,
sense.
not yeah, normally how people think is like, okay, if a less percentage of flux is lost also, it's okay. That's how people usually work, because you can't go below a specific limit, because there is this issue. You can't go very small resolutions. Like if you can talk to people who do kinetic simulations and all, they would say, okay, kinetic simulations are very good. It goes on very small scales, but you can't do that for a big system. That's why we do MHD and all. So we come to things like you need to kind of, it's a trade-off actually. So what physics informed neural networks can do is like there you don't want to calculate these derivatives in such a way. So you can kind of bypass this issue. That's the idea.
But it leads to another question, that how much flux loss due to such thing is allowable in your like process here?
Yes. Yeah. So what we found was that for a normal resolution that we use, the errors are very high, like around 10 to 15% of flux is lost in. That was what we found in our analytical study. That high number of flux is lost. So yeah, it's a debatable question that how much flux is allowed, but ideally we would say we don't want any flux losses, because any loss is something that's changing the underlying physics itself.
Yeah, exactly.
So usually what people do is people kind of try to adjust this with the diffusion constant. Like you try to reduce the diffusion coefficient, which is not originally like the original value that we know. You try to reduce that because you kind of incorporate that. Okay, there will be a numerical diffusion anyway, so let's account for that also and just reduce the original diffusion. That's how people kind of work with it.
Thanks. Yeah. I guess Sanjeev has a question. He raised his hand, so you can go.
Yes, Sanjeev. Sorry, Sanjeev, I think I can't hear you.
Sanjeev, you can unmute and go ahead and ask. You can hear him, Sanjeev? You can go ahead.
Hi, Mr. Sarkar. I have a question. Like how this system is going to make you efficient in forecasting any solar flux transfer?
Sorry?
Uh, See, we are talking about the solar flux transmission. No? So,
Yes.
how these calculations are going to help you in forecasting these solar fluxes?
Yeah, so we are not interested in calculating the solar plexus, but rather we are interested in uh, calculate or forecasting the active regions itself, the magnetogram itself. So we want the forecasting done of the magnetograms with very less numerical losses or any losses that corresponds to the solvers itself. We don't want to add such losses to the evolution of magnetograms. So we are more interested in calculating the flux of the magnetograms itself very correctly, so that it will be kind of helpful in further forecasting the space weather.
Okay, and if I can recommend that we have some system where we are able to forecast the solar fluxes and solar flares, will that be able to help you somehow? Means your
Okay.
calculations will go even beyond the limit. You will be able to calculate it faster, even accurately. If you know when solar energy is going to gather at a one place at particular place, will that be able to solve your problem or make your
No.
procedure easy?
So, like in this specific case, we are not talking about the laws of magnetic solar flux corresponding to any physical process. We are just finding what the solvers itself is providing, like the loss that is due to the solvers itself, not because of any physical process.
That's good. Thank you. Thank you so much.
Okay, thank you. I don't see any more questions.
Yeah, we can wait for some time. Someone
Yeah,
ask.
sure. Just looking through the
Yeah,
participants list.
I just got another hands up. Ilesh, you can go ahead and ask.
Thank you, sir. My question was just what is the benefit of this system that you are talking about?
Okay, so I think the question is like, what is the benefit of using physics for neural networks mainly? So I would say there are two specific uses that we kind of are seeking. First thing is as I just explained, a better solution with less solver interferences or solver noises. So that's the one thing that we kind of see. And the second thing that we search for that we have not yet attained, but we are still working on that, is the faster computation. Like once you have a neural network setup which can kind of incorporate any initial conditions which we are currently working on, so then we will be able to do the simulations of multiple let's say magnetograms simultaneously. Once the neural network kind of learns the how to solve the equation independent of the initial condition. So that's currently under work, but these are the two advantages that we seek.
No, sir. And my point is that the thing we are doing here, how it is going to benefit us in future. Whether we could forecast the flow of flux, that is more important for us.
Yeah. So this could be used, as I told, this could be used to forecast mainly the space weather events, like the mainly solar wind, because in solar wind studies, specifically I quoted Swasti, they use magnetogram data, which is the initial the magnetic field at the solar surface. So they use the magnetogram data to kind of use different methods like WSA method and PFSS and all those things to kind of find what will be the velocity, the plasma properties mainly, the velocity, number density, and these things at L1 point, which can be further calculated. So for this specific thing, mainly solar wind and all, we need to know what is the magnetogram. So if you can forecast the magnetogram, it means we are forecasting the solar wind. So that's the idea.
Actually, the solar wind is generated from the flux.
Yeah, it's generated from coronal holes mainly. Yes. So we need to know where they are. Like we need to know on the magnetogram or on the solar surface where it is. Like how the magnetogram will be in a future time. Let's say we are talking today. If you can take today's magnetogram and kind of calculate what will be the magnetogram, let's say 10 days after, then we will be able to calculate what will be the solar wind almost 10 plus 2, 12 days after. Sorry. Sorry, your sound
Yeah, I
is
guess
breaking.
his voice is breaking, I guess. Some internet connection issue.
Yeah, I think we can wait for a minute.
Seems like some internet connection issue.
Yeah.
Sanjeev, you have raised the hand, so will you like wanting to ask another question?
Not exactly the question. I'll give you a little background. I am forecasting solar winds and solar flares for last 5 years almost, accurately date by date. Um, uh, yes, I'm also working on the system where I can forecast the intensity accurately. Suppose if it is going to be X class solar wind, then I'm able to forecast it even months and years before it happens. So
Okay.
yes, in future we'll be in touch, Jithu. So
Yeah,
nice
sure.
discussion.
Sure. Sure.
Thank you. Thank you.
Thank you.
You can wait for a couple of minutes. So if someone has any question, yeah. By that time, I guess I can ask you another question.
Yes.
So basically, in your equation regarding the loss function, where you have this epsilon. So there you have mentioned, not epsilon, I guess that's zeta or xi
Yeah.
something.
Yes, it's a zeta.
Yeah, zeta. Yeah, so here you have mentioned the weightage, and those weightage are basically based on the physics of the system, right? So
Not really. What we did is we have a system called a optimization system, where we kind of initially put on the architecture. Like we don't set the architecture by our hand. Rather, we kind of use it's a statistical method actually. So with that, you do multiple runs of the pins network, and you kind of study how the loss are varying. And we kind of try to pinpoint a point. It's like you are using a Gaussian, and you are trying to find the peak of the Gaussian. You do multiple runs, and you kind of try to find, okay, at which point you have the best result. So it's you can say it's kind of, it's not a trial and error. So I can't say trial and error. It's a statistical method of finding these values on what will be the best value.
So it's basically optimization process using
It's
like
a optimization process.
Okay.
So we obtain all these values from optimization process.
So here basically where exactly the like physics is involved. Physics means you are using the physical data and applying
yes, I
to
can
these equations.
I can help with that. So
Yes.
in the last one, you see zeta of PD, it's the partial differential equation. So you kind of run this for like you have a NPD. NPD means how much number of points should we check the equation for, means how good the equation is working for. So this is a number that we know, and this F correspond to the equation. So the F is like you have an equation, the SFT equation, and it should be equal to 0. So the F corresponds to the SFT equation itself. Now we are trying to make the SFT equation closer to 0. Now why 0? I can show it on the equation. We kind of take all these terms to one side, and we take equal to 0. So that is what is F is.
Okay.
So F is equal to everything, all these terms in one side. So ideally F should be equal to 0. So it's actually, it's like you have to put F minus 0 mod square. You are trying to make F closer to 0. That you are forcing the equation to be fulfilled.
I see. And from there you get the values actually.
Yeah. So this gets the equation part inside.
I see.
Yeah.
Nice.
I think I should have put the F part also here.
No, it's okay.
Yeah.
It's a nice work. Nice work. Yeah.
Thank you.
Because like in our case also we need the like since currently I'm working close to the sun, so we also need some parameters which can help us to forecast the evolution of the active regions so that we can predict the things which are associated with active region, for example, flares and other things.
Yeah. I think Nilesh.
Nilesh, raised his hand. Yeah, you can go ahead.
Thank you once again, sir. Actually, I was more interested to know how the flares, when flares are coming, the forecast for the flares.
Okay. So, yeah.
But this because magneto is coming after that storm is coming after the fluxes, and I hope so one day you are also going to predict that also. So, right now, NOAA is also using for forecasting storms that is coming to the Earth. So, what is the difference between your and NOAA?
Yeah. So in NOAA, I think we don't do any flare forecasting in this. Like we kind of maximum that can be done is the magnetogram, which kind of helps in finding the solar wind. So it has nothing to do with the, like, we don't forecast solar flares or CMEs also. We don't do any forecasting in that sense. we do forecasting in this. We try to do forecasting in the sense the magnetogram, which then can be connected to the background solar wind. That's what we do. And to my understanding, I don't know if NOVA is. I'm not sure what NOVA uses for solar flare prediction. So I think
No,
I'm
NOAA
not a good.
doesn't. No, sir. My question, NOAA is also doing for that solar storm that going to hit Earth after a solar flux. So my question was how different your system and NOAA system for magnetometer.
Okay, so NOVA, as I understand, means not sure. They would be also using SFT. As I know, Adapt is using SFT itself to kind of SFT plus some setups to incorporate the background also. So that's what Adapt does. So I'm not exactly sure what NOVA uses, but it should be SFT itself, I think.
So we could compare your system with NOAA system.
Okay, currently we have the magnetogram setup only. So yeah, it could be a project, but it would require some things to be done in between.
Okay, sir. Thank you. Thank you very much.
Okay, thank you. Yeah, Pratik.
Yeah, I just wanted to add to the previous question. I think for the magnetograms far side, NOVA is mainly dependent on the adapt. However, I don't
Yes.
think they use pin for that, which you are using. Yeah.
No, they use SFT and like Adapt uses SFT itself, the same setup, the numerical setup. Yeah.
Yeah, it's purely numerical thing. And
Yes.
Kalman filter and these things, they're a
Yes.
little complicated one. Yeah. And for storms, they are basically using WSA Enlil, that thing.
Yeah.
It seems like there are no more questions. If anyone has any last minute question, just can go ahead, unmute themselves and ask. It seems like there are no more questions. So we can once again applause to Jithu and his work. So yeah.
Thank you, Debesh.
Yeah,
And
virtual.
once again, happy Diwali.
Yeah, thanks, and same to you. Enjoy your Diwali. Yeah.
Yeah, sure.
So yeah, so we can then stop the meeting. And Pranodipta, you can just